Okay, so thank you very much to having me here. And so this is work done with a student at the University of Iowa and also people at NCSU and Syracuse, supported by the Department of Energy and the QCAN award. And so I wanted to thank all the office hour people, and so it's a pleasure to have Kelly, Jan, Dan, Eva, and Ermal, Milan, and Pedro. So it has been great to work with everybody and so learn more about the hardware and a lot of interesting details. And so the goals are to study the critical behavior of squares arrays. And so we are interested in using square array for gauge theories, simulation of lattice gauge theories, and we are interested in studying conformal field theory in 2+1 dimension. And we have made good progress in extracting the entanglement entropy on the bit strings, and we have a detailed understanding of all the weakness and strength of Quera. So the main challenges that we have encountered are the sorting fidelities, the readout error, adiabatic preparation, and things that I don't really know how they come from, but so they play an important role, so which are the position and calibration of the treatment. We have spent most of our resource, and we would certainly welcome more if there are opportunities. And so we had, so the result can be found in 2 published papers and 2 preprints that are available. And so the motivation, so the physics motivation is to, for me, do real-time evolution with a strongly interacting particles. And so that's something that is important for collider physics, where currently you have event generators that are big business in high energy experiments. So 20% of the computing budget is spent on event generation at CERN. And so currently they have a very simple empirical model for fragmentation. And so this is the Lund model. So this is an illustration. And so this is a also very simple 1+1 dimensional model that was done with exact diagonalization. And this is a simulator with Quera or Rydberg atoms that reproduce some, but not all, of the properties of the model. So this is the big plan. So the talk by Siva was very inspiring from this point of view, because we have to prepare state with a lot of particles. So we go at delta positive, and then we have to evolve with delta negative. So the transition and the peaks that he mentioned are very interesting to me. So, so the model that we are working on is a spin chain. So it's in principle it has states, it has a discrete electric field, and the quantum number go from -infinity to +infinity. But for practical reason, we truncate to m equal ±1 or 0. So it's a spin 1, and I realized this with a blockade mechanism and 2 Rydberg atoms, but we have been playing around with the blockade, and so the blockade is not dictatorship. The dictatorship of the blockade comes with other consequences that I can discuss privately. But so we have a kind of a loose blockade at the end. So so this is a side remark, but so if you go down 10 minutes, there is the QT, and there will be a speaker from the QT that will talk later. But so this is a way to simulate this model without without the analog method that we are considering. And so I will visit NOAA later in the day. So if anybody is interested to join, let me know. So now I'm very glad that Siva has introduced all these things. So we have Rabi tuning and the geometry. So these are the three things that we can do. And so the blockade, so each of the rungs in the ladder are spin 1. And so at the beginning of the construction, I assumed that they were like they were very close to each other, so the blockade would be absolute, but then we relaxed a little bit the scheme. But so the scheme is M0 is a ground, and then Rydberg ground, and the ground Rydberg are the plus or minus 1. So this is an analog system. And so we wrote a effective theory for the simulator, and so I guessed the simulator from just looking at it, but very nicely, I got all the term from the target plus one extra term that kind of changes the phase diagram, so I relaxed this constraint a little bit. The target is much with a negative detuning, but the positive detuning can be used to prepare very interesting initial state. So I will mostly speak about the positive detuning. And so it has a very rich phase diagram. And so by working with Aquila, we were able to produce the first experimental demonstration of a floating phase. And so that was a really fun experience for theorists. And then, so I will talk a little bit about the phase diagram. And so Siva has already introduced it. So it will be RB over A versus delta. And so we will, typically we work at a fixed lattice spacing, and then we vary delta and omega. So we take the lattice spacing as small as we want, as we can, as we want. And so one observation that I made in this process is that the phase boundaries in this phase diagram obtained with the bit strings and obtained with the full wave function, so with the DMRG. So and so you lose the phase information when you use the bit string, but the two phase diagram are very similar. And so this is the phase diagram for the entanglement entropy. So this is for the ladder with a it says aspect ratio of 2. So the rungs are twice longer than the lattice spacing. And so this is from the wave function, and this is from the bit strings. So this is extracted from just the correlation in the bit string. And so you see that they are very similar. And so getting the entanglement, so when I talked to the experimentalist and I said, could you measure the entanglement entropy? They say, yes, we can, in principle, make these copies, but it's a very expensive process. So my guess is that I should be able to get the entanglement from the bit string of a single copy. So this is very cheap, and you can get this for Quera, but for any device that produce bit string. So you can it's very generic. A nice thing is that theorists can run Quera without help. They don't need to get on the waiting list of somebody famous. And so you can, all you need is a credit card or a QCAN account. Now I was very proud to be able, so I wrote a single outer paper to show that you can do it without any money. Then I submitted to a journal. They say I could not call it an experiment. But, so it's a rubidium. Anyway, so the output bit strings, and so I used a lot of Shannon technique to analyze the bit string because they are classical objects. Like message, and so now the great deal to understand is what are the errors, and then can we do something good with only 1,000 shots? So in lattice gauge theory, you can get good result with 1,000 configuration, and so the answer is that yes, we can, at least for reasonably sized system, for the system that we can simulate now, it's possible to get good result with 1,000 shots, which is a $10 in the era platform. So it's very, so for those of you who have never used Quera, it's very easy. So you could teach a high school student how to do it in half an hour. All you need to do is to fix the geometry of the atoms, have the omega time profile and the delta time profile. There's also a phase, but I don't use. You run it. This is a 100 shots. The cost is $1.30, and then it spits the bit strings. So the R are Rydberg and the G are ground states. That's very easy. Yeah, so that was the comment by PhysRev A that we have to call this demonstrations. So I avoid that name because in a demonstration, you know the answer in advance, and in what we do, we don't know the answer. So it's, I call this remote operation of Rydberg atoms. So that was so my first use of Quera, and so I just so while I was working with the Quera team for the floating phase, I got bit string to play with, and so I tried to mimic what we do in the quantum case with the classical probability, and so you can have reduced probability. And that was invented by Mr. Bayes and Mr. Lagrange a few hundred years ago. But then Shannon, I realized that, so if you look at the Shannon entropy of the full system or the Shannon entropy of the reduced R system, they are in about ratio 2. So by taking twice this minus that, you get the black, which is just right under the quantum entanglement entropy. And so I found this empirically, and then I realized that somebody had proven this. So it's called the O-level bond. And so now this is the mutual information of the bit string with exact diagonalization. This is the von Neumann entropy with exact diagonalization. I kept delta constant in a 10 atoms chain, and I vary the RB over A. And so I got $200. I got 20 data points, which are the empty symbols, and 3 with the full symbols with the local simulator. And so you see that it's a pretty good estimation of the quantum von Neumann entropy. And it's a dirt cheap. So this is $200 compared to putting two systems together, which I think Quera people should be able to do now, but it would be very complicated. Now, question is, how tight is the O-level bond? And so you can see that, so this is the entanglement entropy, this is the mutual information, and this is the ratio. And the bond is very tight when the entanglement is high and not very tight when the entanglement is low. So then I had the chance to make something not optimal, but I learned something from it. So if you look at the AWS tutorial about the ramping down, this is copied from the AWS. They say to do that in a half microsecond. And if you do that, it's almost adiabatic. And now it had an unpredicted consequences that it enhanced the high probability compared to the low probability, and the bound got closer to the target. So by doing something wrong, I got something right. And then I did it with my student in a very controlled way. So we filtered the probability. So we removed the low, count probability, and then we redo the visual information with a renormalized probability. And so we get now so this improves, but you have to know how to stop. And then another very nice observation was made that by looking at the conditional entropy, you can just find the right spot to get the visual information to just hit the right value. So this is a summary of this. This is the mutual information, and this is the von Neumann entropy. So I want to get this. If I don't filter, I have the Oliver bound, and then when I filter, it goes up and up and up, and it goes over. But if I look at the conditional entropy here, I fit it with a sigmoid, and I looked at the inflection point. It hits the target in a remarkable way, and it blows my mind. I don't know why. I thought I was lucky. Then we try many other cases, and in most cases, it always works. So there's something behind this that we are trying to figure out, but it's very efficient. And so this filtration means that you don't need too many bit strings if your system is small enough. So then that was done with a numerical calculation, but we can also do it with Aquila. And in the process, we learned about the errors. And so these are the Aquila errors that I understand. So there is the sorting fidelity. So you have some initial state that are not right. You have the adiabatic preparation, which is limited to 4 microseconds. You can go higher, but at your own expenses. And you can go up to 20 now, but it's not as good as the fidelity with the even time preparation is not as good. The ramp down, as I mentioned, has to be much faster, and that solves the problem. And then we have large readout errors that are typically 8% for reading a Rydberg into a ground state. And AWS people monitor this, and it varies in the day. So it's like IBM, but we don't have the record. You can do it yourself. It doesn't cost too much, but and so this is, so the nice thing is we get the raw data. So I like to get the raw data. There's a pre-sequence, and so the pre-sequence should be all ones. So that's the experimentalist convention. The ones are ground state. So this means that there is no atom, and so you can throw it away or you can keep it depending on what you believe is the right thing. Now I have to, so I've done 4 sets of calculation in October, blue, 24, January 25 red, May 25 orange, and July green. And so this is the fraction of starting configuration that are correct. And so as you increase the size, it decreases exponentially, but you see that with time, so you have, the team at Aquila has made remarkable progress in getting the sorting fidelity much better. So then the adiabatic preparation, so I have a student who optimized the ramp up by moving the three parameters, and so he was able to improve the fidelity of to the ground states, and we also used the M3 correction for the readout errors. That works very well. And so this is an example. The goal now is to get the square. So this is for a 3x3 square. And so the black are the exact probability. The blue are the Aquila with our original ramp up. Then M3 are purple and the local is green. So this is not very good. Then with the improved ramp up, we got something that is significantly better. So we are still working on improving this. Then the goal was to get this multipartite entanglement that people study in the CFT. And so they have a weak and a strong combination of multipartite entanglement, and we estimate them with the Shannon version, which is called H, like in Shannon's paper. But you will see that there are 8 of these Shannon piece for the weak and the strong, and I thought it would never work, but it does. So first, so this is numerical. This is for the Ising model. So this is a bipartite entanglement, and this is the multipartite entanglement, and it spots the transition in a very neat way. And the filtering works. This is crazy. And so this is just an example of, so the dash Aquila, and so we filter, and so again we use this conditional entropy, and we get really close to the target value. And so I think time, so the 2-leg ladder is a very nice analog simulator. So we can estimate the entanglement with the bit strings. The filtration with an optimization works very nicely. We understand almost all the errors, and so we are looking forward to go to a larger system. And we also work with people at Syracuse and at CSU about these larger squares. Thank you very much.